So thank you very much for inviting me to this Oceanics, is that right? The project.
Oceanics.
Oceanics, okay, Oceanics, okay. I didn't know how to pronounce. And I'm very happy to present our recent work on data simulation, and we also have a new computer, Fugaku. That's the Japanese national flagship, the biggest supercomputer, and it's ranked #1 right now. And I hope that it will keep #1 position for a while. So let me first introduce myself briefly. So I graduated from the Kyoto University, and then I went to JMA. I worked for the JMA. JMA is the Japanese Meteorological Agency. That's a weather service in Japan, the operational weather service in Japan. And I did the administration work for the initial 2 years. And then I started developing the data simulation system for the operational numerical weather prediction. And then I had a chance to study at the University of Maryland. I had a bachelor's degree from Kyoto University, and I had a chance to study at the graduate school at the University of Maryland for 2 years. And I finished the PhD in these 2 years, mainly because I had the already experience of the data simulation development at JMA, and I knew what I would like to do at that time. So that's basically finding a good research topic for PhD takes time, but I skip all the time for looking for the good topic. So I developed the ensemble Kalman filter, LETKF, the local ensemble transform Kalman filter system for my thesis. Then I went to JMA again to apply the local ensemble transform Kalman filter, the LETKF, to the operational JMA weather prediction system. And then I moved to the University of Maryland as a faculty member, and I was an assistant professor there. And then more than 8 years ago, by now, I moved to RIKEN Kobe, where we had the previous big supercomputer, K computer, and we made a lot of progress using the K computer. So my talk today includes some results from the K computer, as well as newer results with the Fugaku, that's a new supercomputer. Okay, and so my team, the data simulation research team, has about 15 scientists, full-time postdocs and mid-career scientists working on various topics on data simulation, but mainly focusing on numerical weather prediction mainly because of my background. So we had, as Pierre already mentioned, we had the IMT-Atlantique and RIKEN joint workshops. This is the web image from the previous year, the last year. Almost exactly 1 year ago, I was in Brest. It was very nice meeting about, here is the topic, the statistical modeling and machine learning in meteorology and oceanography. And we, so doing the new series this year, because of the COVID-19, we couldn't travel around, but we would like to keep our active collaboration. So we planned online seminar series like this. So today is actually jointly with this Oceanics project. I am the first speaker of this seminar series, followed by 5 seminars every time. Okay, so the next one is seminar 2, application of deep learning methods to environmental data. And we identify the speakers and we are filling in these missing parts. But every time we have 30 minutes talk from IMT-Atlantique and from RIKEN side, and followed by 30 minutes discussion. So 1.5 hours for every seminar. So we have up to 5, and the last one will be given by Pierre. So on April 14th. So I will come back to this because this is related to my talk. Okay, so we started developing a unique numerical weather prediction system using the K computer, and we started developing this system in 2013. It's already about 8 years ago. And this was a strong motivation to think about what we should do with the supercomputer. So this river is in the city of Kobe, and this river became like this only in 10 minutes. This is the actual image of the live camera. And 5 people died at this time, unfortunately. And if we can predict this type of very small scale convective rain, even 10 minutes before it happens, we could have saved these lives. So that was a strong motivation. So what we had at that time was a K computer, so that we had very powerful computing power. And we also had the new sensors, like the phase array radar, like this one, producing 100 times of more data than the regular radar system, or this Himawari geostationary satellite. The new generation Himawari 8 was launched in 2014 and started the operational observation in 2015, and also producing 50 times of more data than the previous generation, higher resolution and higher frequency in time. So we thought about how to use this big data effectively to make those predictions. And we spent about 3 years for the initial development, and this is a successful, finally we succeeded in assimilating this every 30-second dense volume scan. This is the observed image, and this is what we produced in the computer. So every 30 seconds we get the data, and we assimilate the data every 30 seconds and make 30-second prediction. It's not minutes, it takes seconds. 30 seconds prediction, and then get the new data. So it's really was a challenge. So this movie shows that we had a very successful computation of the data assimilation. So you can see that this movie on YouTube. So you could take a look later if you're interested. You can stop or look more carefully. So we have more than 42,000 views at this time, and it was ranked top 10, but now I checked and it was ranked number 11 at this time. The RIKEN channel has more than several thousand contents. So ranked number 11 is already very, very high compared with the number of content. So again, this is the observed radar data, and this is what we produced in the computer. So this is virtual, this is real. And the bottom left here is the simulation that we produce without assimilating this observation data. So this is supposed to be the normal, regular weather prediction. So we cannot really capture this type of rapidly developing system. Because we have every 30-second data, we can produce this system in the computer very well. So this is what we achieved. And last year, we had a chance to do the real-time forecast every 30-second refresh. During this period actually corresponds to the Paralympic Tokyo Paralympic game was supposed to be held during this period, but because of the COVID-19, the Tokyo Olympic and Paralympic Games were postponed, but we arranged the exclusive use of a supercomputer of the University of Tokyo because the K computer was already shut down. So we had to use another powerful computer, the one in the University of Tokyo and Tsukuba University. We arranged the exclusive use of part of the supercomputer to make the real-time prediction. So I will talk a little about this. So as I said, we planned to do the real-time prediction for the Tokyo Olympic and Paralympic Games. So we used the new phase array weather radar. So this is a multi-parameter phase array weather radar developed in another project called SIP, that's a national project. They developed a new type of the phase array. And this is located here in Saitama, right north of Tokyo. These dots here represent the Olympic and Paralympic venues. So this is well located to capture the rain within this 60-kilometer range, covering most of the venues. So we applied our system to that, and as I said, this is the web page of the University of Tokyo Supercomputing Division, and we made a special arrangement for an exclusive use of this Oak Forest PAX. That's the name of the supercomputer of the University of Tokyo and Tsukuba University. And we developed a real-time workflow. We get the data real-time from NCEP GFS, that's a global forecasting system. And we get like 9 hours delay from the real time, and then we run our system using this as the boundary condition. And this large domain 1, this domain 2, that's a 6-kilometer mesh, run simultaneously, and then that will provide the boundary condition for 1.5-kilometer mesh domain 3. This is the domain. And finally, this will provide the boundary condition for this innermost domain 4 at 500-meter mesh. So here we get the real-time phase array radar observations, and every 30 seconds we run the data simulation and 30 minutes forecast. So this shows the job scheduling. So this is a number of nodes that we secured on the Oak Forest PAX supercomputer, and the time goes this way. This is the 24-hour period. Every 6 hours, we get the updates from the GFS, the NCEP GFS global forecasting data, so that we initialize the domain 1 and domain 2 and domain 3, and these are the up to domain 3. And then this will provide the boundary condition for domain 4. So the domain 4 is the innermost domain and takes most of the computer time here. So this is the number of nodes. We use most of the computer power for the domain 4, of course, because of the high resolution and high frequency data simulation. So this is a past case and showing the promise of this method for weather prediction. So we focus on this rain system here. This is the actual JMA operational nowcasting system, 10-minute lead forecast. We see some rain here, but this rain was actually very strong. This is the actual observation from phase array. And this is the prediction of our system, 10-minute lead, the same 10-minute lead, but we can predict this rapid development of the heavy rain. Because we use the numerical weather prediction model, that's a process-driven model, can predict the rapid change of the rains. So this nowcasting is a data-driven basically, and cannot predict the change, the rapid change of the rains. This is an optical flow-based system. We disseminated the prediction data through the smartphone app so that people can access the prediction data easily. And also we had our RIKEN web page showing this real-time prediction like this. So this is Tokyo Prefecture, and this is a metropolitan part of Tokyo, downtown. So we had a heavy rain passing on September 2nd. And this is the snap, well, the actual web page image. So this shows the whole period of our experiment for about 10 days. And these gray parts, we had some trouble so that the system couldn't produce prediction. But this shows the lead time of 30 minutes forecast. And most of the time, the lead time stays in 26 to 27 minute period. And this is a histogram. We issued total 30,000, more than 30,000 predictions, because every 30 seconds we issue new prediction. So even only in 10-day period, we had 30,000 predictions. Most of the time, more than 99% of the time, the prediction had a lead time more than 26 minutes. That means that we spent only 4 minutes or less to process, to produce the 30 minutes forecast. That was very successful. So we are now verifying more carefully about the data that we had in the real-time experiment and try to publish the results. And then we now try to improve using the new Fugaku supercomputer. And because the Tokyo Olympic and Paralympic Games are postponed to 21 this year, this summer. So at this moment, we are still planning to do it in this year with a new system. Okay, so in general, the data assimilation is something like this plus sign to combine the observations and simulations and add value. The observations are the data, and the simulations are the process, the equations basically, and we compute the equations and to get the prediction from the process-driven approach. So these are completely different two approaches. So data assimilation combines these different approaches. That's how we add the new value. So the workflow of the data assimilation is like this. So we have a simulator. Again, this is a process-driven. So if we put the initial state, then this computes, the simulator computes the evolution based on the process equations, and then produce a simulated state. And once we observe the real atmosphere at this time, then we get the observation corresponding to this simulated state. So then we can make the feedback to combine these two information, the independent information, to produce the best estimate. So this feedback loop makes the whole system more accurate. So the traditional science, what we did was to understand the data and get the knowledge, the human knowledge from the data, and that will, well, that produce the equations for the process or understanding about the process, and that contributes to developing a model for the simulation. So that's a traditional science. So if we think about the scientific methods, as I said, we first understand the observations. Usually the observations or the experiments have the data, those are noisy or missing. So we understand these data by dealing with these noise or missing parts, then get the fundamental laws or the basic knowledge about the process or the mechanism of this data, behind this data. That's a human knowledge. That's known as the experimental science, as the first science. And then the theory, if we understand the theory, then theory provides more knowledge. So that's a theoretical science, known as the second science. And based on the second science, we can describe the nature by the equations. And once we have the computing power beyond human ability, that's the start of the computational science. So we can compute those equations, and that can simulate the real nature so that we can observe what happens in these equations computationally, then that produces a new knowledge, and that feedback to deepen our knowledge or understanding about the fundamental laws. So that's the third science. And more recently, we have the big data beyond human ability. So we have the observations that we cannot look everything, or we have data from the simulation beyond human ability, and just using the machine to process the data or analyze the data, we get the new knowledge. That's the data-centric science known as the fourth science. So if we think about data simulation was like a bridge to connect the observations and simulations. So if we think about the human knowledge and the machine based on the data and the computation, then maybe the data simulation can provide the new paradigm to combine everything. So that's the idea. So we have this data simulation workflow. So I opened up this part. So what we did is to simulate the observations in this simulation, because the observations may not be necessarily the direct observations of the simulated state, but some function of the simulated state. If we think about, for example, the radar data, as I showed, the simulation usually does not produce the radar data in here, but it produces the rain amount in some grid of those. And we need to convert or observe the simulated state from the simulated radar. So this is the radar simulator. Then we can take this actual radar data and compare with the simulated radar data. That's how we assimilate these observations. It's the same for the satellite data, because the satellite data is not simulated in this process-driven simulation. What we need is here, we can use either the process-driven, physically based radiative transfer model to simulate satellite observations of radiation, for example. Then we can combine with the actual radiation observations, radiances from satellites. That's how we assimilate these data. So as long as we have this green box, we can assimilate these observations. So what we do here is to combine the forecast data with the observations, and that data simulation will produce the better analysis, the best analysis based on these errors. So the data simulation is considered as the mathematics of the errors. So it provides some probability distribution of the forecast and the observations, and the Bayesian estimation gives us the multiplication of these two independent distributions. We provide the merged information. So the merged information, if we have two Gaussian distributions, the merged Gaussian distribution is narrower and higher peak. So that's by theory, it's true, but if it's non-Gaussian, it's not necessarily be true. So so in data simulation, representing the distribution is the most essential. That's why using this computer power of the K computer previously, we ran 10,000 ensemble simulations, or the ensemble data simulation, to represent that probability distribution. So each individual dot here, we have 10,240 arranged like this. This is done by Kondo-kun, now at the Meteorological Research Institute of JMA, but he was a former member of my team. And using 10,240, of course, we can represent the probability distribution, in this case, 3 peaks, very well. But if you have only like less than 1,000, well, 640 is still big. If we think about each individual simulation corresponds to the entire atmospheric simulation, 640 is still big. So the regular size may be 80. Then we don't have 3 peaks. We see 2 peaks, but it's kind of not very precise. So high precision distribution can be obtained by running the large ensemble. So this is a non-Gaussian measure by the Kullback library divergence. And we see that the high non-Gaussianity appears mostly in the tropical regions and some mid-latitude region in the storm. And if we reduce the ensemble size, this is really noisy, just a noise from the sampling. So the sampling is really important. To represent a non-Gaussian distribution, we need at least 1,000 ensemble members. So that's the base why we choose more than 1,000 members in our experiments. So what we have done with this K computer was to push all the limits of numerical weather prediction to, well, basically 2 orders of magnitude bigger computations, like 10,000 ensemble members compared with 100, typically 100 ensemble members is 2 orders of magnitude bigger. And the updating cycle is 30 seconds, but usually like 1 hour cycling. 30 seconds is 120 times faster. And the resolution was 100 meter mesh in our convective scale. And compared with 1 kilometer mesh, it's 2-dimensional mesh in the horizontal. So it's 100 times more grid points. So these are basically 100 times bigger computations and try to explore what will be the future of the numerical weather prediction. Now we have Fugaku. What's the difference? What's unique in Fugaku? The Fugaku looks like this. And what's different is that the K has more boxes compared with Fugaku. This is exactly the same space, the same room on top of the 6th floor of the RCCS, our center. And we have fewer boxes and bigger, but this is just physical appearance. It's not very important. So it looks similar, but the biggest difference is the architecture. So the K was not suitable for machine learning. Machine learning usually requires the reduced precision arithmetic computations. So we use, for example, half precision or integer computations, but the K it was designed for good for the double precision or those floating point arithmetic computations. So to do the machine learning, we produce a lot of data from big data simulation or whatever, the high performance computation on the K, but we need to move the data to the suitable computer for machine learning, like the GPU machine. So, but if we have a big supercomputer and process a lot of data and run high resolution and large ensemble simulations, produce huge data that we cannot move or we cannot even save. But we can run the machine learning on the same machine. That means that we don't need to save. We just use the data on the fly in the machine learning algorithms. So we run a big simulation or data simulation and produce a lot of data and run the machine learning on the same computer. So that's the main difference. Okay, so we have a number of ideas to include how to use or integrate the machine learning methods within the data simulation framework. The idea is to run this big computation data on the same high-performance computer, like Fugaku. So one thing that we have been exploring, mainly by Otsuka-kun, maybe he's joining today, we have the neural network and takes the actual observation data, the time series of past observations from the radar that can produce the future data based on the previous data. So if we train the neural network with the actual data, we can make the forecast purely based on the data. But we can improve the prediction if we use the output from the numerical weather prediction. The numerical weather prediction produces the future data. So we can put the future data here to combine with the past time series of the data. And this trained neural network can produce the improved forecast. This is one example of the combination of the machine learning, data assimilation, and simulation. And we have some initial tests using the LSTM, the convolutional LSTM, with the scale that's a numerical weather prediction system, and that produce the best skill of the heavy rain forecast. So higher the better. So this is the highest most of the time, except for this very initial time. So this is good. And another idea is to develop a surrogate model to emulate the simulation here. This is very expensive. As I said, the high resolution model requires a lot of computation. That's why we need to secure a large amount of computing resource for real-time prediction. And that is very expensive. But to use a high-performance computer offline doesn't require having the exclusive allocation of those computer resources real time. So that will make things a lot easier. So the idea is to emulate this high resolution outputs by the neural network. So this method here, using the convolutional neural network, is purely data driven. So we run this high resolution model offline and get a lot of the output data. And then we train this neural network using this data. Then if we put the data here, then that will produce the prediction for this high resolution model at a lot cheaper, a lot less computational complexity, basically. But this is difficult if you have a high resolution model, very complex model. So another idea is to use a low resolution version of the model, still process driven, but it's not as well represented like the high resolution model, but it still has some process inside. Then we fill in the gap between this high resolution and low resolution model by the neural network. So this is a hybrid approach, so hybrid physical statistical model approach. And we compare these two approaches like this. So this is the accuracy of the prediction, and this is a chaotic dynamical system. So even if you have a perfect model, the prediction skill will drop in time. So we don't have a comparison with the perfect model. We should put it, but at this time we don't have it. So we have this purely data-driven method. The skill drops quickly. But this hybrid model, just ignore this blue one. The hybrid, the green, the skill lasts longer. And I think that this is similar to the perfect model. The computer time is a lot faster, like this. So this is running the high resolution model takes this much time, but we can reduce the computer time by the data-driven approach, or the hybrid approach requires running a low-resolution model, but the low-resolution model is very fast. So the total computer time is like this much, so much faster than the high-resolution model. So we would like to apply this approach to our 30-second update prediction system. Then we don't need the large allocation of the high-performance computer in real time. So also we would like to predict the model error. That's a mismatch with the observation data. So we tested the idea in a simple system, but this is the general framework. So we have a model here that will evolve the state in time. Then we get the forecast data, and we get the observation to combine with the LETKF here. And then we get the analysis by the Kalman filter equation. Okay, so this is the RIKEN. So what we include here is the bias correction. So we have the forecast here, but we have the biased forecast. So we correct the bias by estimating the bias using the recurrent neural network in this case. We use the LSTM for estimating the bias, and this shows the error, so lower the better. And this goes time, so this is a prediction. So the lowest is this LSTM. Comparing with this no error correction, no bias correction, this blue one, it's much, much better here. And all the other lines are the linear bias correction or other methods for the bias correction, the polynomial, fourth order polynomial bias correction, but LSTM can represent the non-linear relationship with the state so that we can correct the model bias even better. Another example includes this observation operator. So for satellite simulator, we usually use the radiative transfer model. So we convert the model variables to the satellite observations using the radiative transfer. But we replace completely this radiative transfer model with a neural network. Then we have an accurate prediction using this neural network, and that it shows the method really works. So this shows the analysis error, the temperature error at different levels, and slightly worse, but it's good. As the first test, it's very successful. So this is my final slide. The idea was first to use the AI techniques or the machine learning in data assimilation framework, but we know that these statistical methods, that DA is also a statistical method, and I think that we should think more deeply about fusing in the algorithmic level the AI and DA with the big data and the big computer. So I think that will be the one of the future possible directions for the new meteorology as the fifth science, as I introduced the scientific methods. Thank you very much for your attention, and I would be happy to answer your questions.